In this video we are going to introduce the notion of linear stability of numerical solvers for ordinary differential equations. And we are going to do so focusing on a particular example, which is kind of a prototype of a bigger reasoning, and this is the one of the damped harmonic oscillator. The equations of the system we study today are written here. So we have q double prime, where the double prime stands for the second time derivative, plus gamma q prime plus q is equal to 0. So q is the position of a point mass, which is connected through a spring to a fixed point, like the origin. Q prime is its velocity, and q double prime is its acceleration. So we are assuming to have unit mass and also unit spring constant, whereas gamma is a positive scalar determining the damping coefficient. Since the dependence of these equations over q and q prime is linear, we can rewrite this into a system of two scalar ODEs, which are linear themselves. And more precisely, we can also define a matrix A just by isolating q prime and q double prime, or v prime if you define q prime is equal v, which is x prime is equal ax, with a defined by the terms appearing in this ODE here. So this is the system we are studying, and we consider this format here. What we will see now is how we can simulate the equations of this system, and why for some choices of numerical methods we need to be careful on how we pick the time step, depending on the scalar value gamma in particular, but more generally on the properties of the matrix A. Being this system of ordinary differential equations linear, we know that we can exactly solve it, and the exact solution is the action of the matrix exponential on the initial condition. But still we are interested in understanding in this simple setting how numerical methods behave, if we need to be careful in how to pick the time step, for example. And we compared three numerical methods, which are pretty standard, and they behave in a quite different way. So the first one is the simplest method possible, it's just explicit Euler. And being the system linear, we can fully characterize it through the action on the current position, xn, of a matrix, which in this case is nothing else than the identity plus h times the matrix A, defining the dynamics. For the implicit Euler method, instead, we need to solve a linear system to define the update from xn to xn plus 1, which in this case is just a linear system, in general is the solution of a nonlinear equation. And we say that xn plus 1 is equal to the inverse of I minus ha times xn. And this is well defined as long as h is small enough, in the sense that this matrix is invertible, being a perturbation of the identity. And then there's a fourth order method, which is a classical Runge-Kutta method, that you can see implemented in several libraries. And in the case of a linear system, it simplifies to something pretty explicit that I wrote here. And all these matrices here that we multiply from the left with the current position xn provide a different degree of approximation of the exact solution, or the exact updating map, updating matrix, which is exactly the exponential, matrix exponential of h times a. The exploration we will do from now on will be mostly based on the eigenvalues of the matrix A, because those are the determining factor of the behavior of at least two of the three methods we saw before. So just to have a clear idea of what are actually the eigenvalues of this matrix, here is a derivation. So you can see that we started from the matrix A defining our system, which is parametrically depending on gamma. And the eigenvalues of this matrix can be written as lambda plus and minus, and they are written in this form. So you can see that clearly gamma squared minus 4 is a determining constant, or a quantity that we need to keep track of. In particular, if gamma is smaller than 2, then what we get is that we get complex conjugate eigenvalues. In particular, we still have a negative real part, and that's what is giving damping. But then we also have a non-trivial, non-zero imaginary part. Then we have the limiting behavior, the intermediate behavior, where gamma equals 2, we have two identical real eigenvalues, which are real negative eigenvalues. And then there's the other regime, which is the overdamped regime, where we have gamma larger than 2. And then in this case we have two distinct eigenvalues, which are both real and both negative. I created an interactive plot which allows us now to explore how h and gamma relate with the good or bad behavior of the three methods we have introduced. So you can see first of all that with gamma equal 2, which is the critical value we identified in the previous slide, we have that this point here, which is the same in all the three plots, is placed on the x-axis, which is the real line, because the imaginary part, which is the y-axis, is equal to 0. What I'm plotting here with this red point is just the eigenvalues, the 2 eigenvalues in the complex plane of the matrix H times A. So it's just a rescaling of the -1 we got before by the value of H. So you see in particular that whenever we get, for example, to 1, we will get to a value which is -1, 0. Now, what you can see on top is instead the solution produced by the 3 solvers, the 3 methods, with that particular choice of gamma and that particular choice of time step. And we compare it with the reference solution, which is just the exponential, which is over here. So you can see here that in this particular case, whatever H we pick, at least in this range, there's no bad behavior, there's no blow up of the solution. Now, what happens instead if we try to increase the value of gamma? And increasing the value of gamma means essentially that we will be quicker at damping. So you can see that the more gamma grows, even just gamma equal 4, the worse the solutions of the 2 solvers become, the 2 first solvers become. And you can also notice at the bottom here that the points depart, differentiate, and we know that this is the case because with gamma larger than 2, we have 2 distinct real and negative eigenvalues of the matrix. So that's why we have 2 points. But one of the 2 points leaves this region for both RK4 and explicit Euler. So this region will not be introduced and formally characterized in this video. I will dedicate a separate video to it. But it's the so-called stability region, and each method has its own. But you can see that implicit Euler has the full negative part of the plane, so the full negative real line, which is included in the stability region. So it doesn't really matter how big gamma becomes, and in fact the solution remains pretty stable, or at least it reproduces the expected behavior of damping towards the origin. On the other hand, RK4 and explicit Euler have bounded regions of stability, and in particular you can always pick a choice of H and gamma which allows us to leave this region and hence blow up and hence not be stable anymore. Now H is pretty large, so if I reduce it, I can always find an H small enough that brings me back to the correct region, and hence the stability or the expected behavior is recovered. But this doesn't mean that if we increase gamma, we get back to where we were before. Now it's clear that RK4 is still a bit better than explicit Euler in the sense that the restrictions are a bit milder. For example, in this case, we have a pretty good solution for RK4, whereas we have a blow up of the solution in explicit Euler. But still we need always to be careful, because if we increase a little bit more the step, we blow up. On the other hand, implicit Euler is still quite good, still reliable. Of course, the larger the step size, the farther we are from being providing an accurate solution. But still we have guarantees that we will not blow up. So this was just an exploration of the properties of simple methods like these 3 solvers that we have introduced. And the goal was to introduce a clear distinction between 2 families of methods, which will be the astable methods, which are like implicit Euler, where there's no need for a restriction on the step size to guarantee no blow-ups, so to guarantee to provide a stable solution. And non-astable methods, like all explicit solvers are, where you need a restriction of suitably small time step in order to compensate for the complications provided by the stiff dynamics, for example by the large gammas in this case. So I will go into the mathematics of this in a later video, but today I just wanted to give this idea, and hopefully this animation gives you enough intuition of what is going on. And if you have any questions, just let me know in the comments. Otherwise, see you in the next one. Bye.